Most people think they know what gravity is. If you ask someone, they will say gravity is the force that pulls things down. Drop a stone, it falls. Throw something upward, it comes back. The Earth pulls on the moon. The sun pulls on the planets. This idea feels obvious because it works so well in everyday life. For more than 300 years, physics agreed with this intuition. Isaac Newton described gravity as a force acting at a distance. Two masses attract each other. The strength of the attraction depends on how massive they are and how far apart they are. The equation is simple, powerful, and astonishingly accurate. Using it, humans predicted eclipses, discovered new planets, and navigated spacecraft across the solar system. In this picture, gravity behaves like other forces. It acts between objects, it transmits influence, it causes acceleration. You can imagine it as an invisible tether connecting masses across space. But even Newton himself was uncomfortable with this idea. He openly admitted that he did not know how gravity acted across empty space. There was no mechanism, no medium, no explanation, just a rule that worked. For a long time, physics accepted this discomfort because the results were so successful. Then, in the early 20th century, something changed. Albert Einstein looked at gravity and realized that treating it as a force created deep inconsistencies. His insight was radical. Gravity is not something objects do to each other. Instead, gravity is something space and time are. According to general relativity, massive objects curve spacetime. Planets, stars, and galaxies deform the geometry around them. Objects moving nearby simply follow the straightest possible paths in this curved geometry. What we interpret as a gravitational pull is actually motion along curved spacetime. This was not just a philosophical reinterpretation, it made concrete predictions. Time runs slower near massive objects. Light bends when passing near stars. Gravitational waves ripple through spacetime when massive bodies accelerate. Every one of these predictions has been confirmed. At this point, it seems gravity has already lost its status as a traditional force. But here is the crucial thing. Even in Einstein's theory, gravity is still fundamental. Space-time curvature is built into the basic structure of reality. It is not derived from something deeper. And yet, cracks begin to appear when gravity is pushed to extremes. When physicists study black holes, they find something unsettling. Black holes behave like thermodynamic objects. They have temperature. They have entropy. They obey laws that look disturbingly similar to the laws governing heat, energy, and information. This should not happen. Thermodynamics describes systems made of many microscopic components. Temperature is not fundamental. It emerges from the collective behavior of countless particles. Pressure works the same way. No single molecule creates pressure. Pressure arises from enormous numbers of microscopic collisions with container walls. From this perspective, temperature and pressure are not forces. They're emergent descriptions, useful, real, but not fundamental. Now, consider gravity again. In black hole physics, the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This was shocking. It suggested that information about everything that falls into a black hole is stored on a surface, not in a volume. This idea later evolved into the holographic principle. The information describing a region of space may be encoded on its boundary. If that sounds abstract, its implication is not. It suggests that the three-dimensional world we experience may emerge from something more basic, possibly lower dimensional, governed by information rather than geometry. If space-time itself is emergent, then gravity, being a feature of space-time, may also be emergent. This is where the idea of gravity as an illusion begins to take shape. Not an illusion in the sense that it's fake or imaginary, apples still fall, planets still orbit, but an illusion in the same sense that temperature is an illusion. It feels fundamental, but it's actually a macroscopic effect of microscopic degrees of freedom we do not yet fully understand. One of the first hints in this direction came from the observation that Einstein's equations can be derived from thermodynamic principles. Under certain assumptions, the equations governing spacetime curvature can be obtained by demanding that entropy behaves consistently with energy flow across horizons. This is deeply strange. It suggests that the geometry of spacetime may be constrained by the same logic that governs heat flow. In other words, gravity may not be telling matter how to move. It may be telling information how to rearrange itself. At this point, the question becomes unavoidable. If gravity is emergent, what is it emerging from? One proposal treats gravity as an entropic phenomenon. In this view, objects move the way they do because systems tend to evolve toward states with higher entropy. Motion in a gravitational field is not driven by force, but by statistical preference. To see why this idea is not as strange as it sounds, consider diffusion. If you release a drop of ink into water, it spreads out. No force pulls the ink apart. The motion happens because there are vastly more microscopic arrangements corresponding to a mixed state than to a concentrated one. Entropy increases not because something pushes matter around, but because probability favors disorder. Now imagine space-time itself has microscopic degrees of freedom, unknown entities whose collective behavior gives rise to geometry. When matter moves through space-time, it changes how these microscopic degrees of freedom can arrange themselves. The motion we call falling may simply be matter moving toward configurations that maximize entropy of the underlying space-time structure. In this picture, gravity is not fundamental interaction. It is a statistical tendency. Objects fall not because they are pulled, but because there are more possible microstates corresponding to their being lower in a gravitational field. This idea remains controversial. It is not a finished theory, but it has produced equations that resemble known gravitational laws, including Newton's inverse square law, under specific assumptions. What makes this idea powerful is not that it replaces gravity with something mystical. It replaces gravity with something familiar, statistics. The same mathematics that governs gases and heat may govern space-time itself. If this is true, then gravity is not a basic ingredient of the universe. It is a large-scale effect, visible only when many degrees of freedom act together. And that would mean something profound. It would mean that when we talk about gravity, we are already talking about an approximation. If gravity is emergent, then one immediate question becomes unavoidable. What exactly are the microscopic degrees of freedom from which space-time and gravity emerge? In ordinary matter, this question is easy. Temperature emerges from atoms. Pressure emerges from molecular collisions. Entropy counts microscopic configurations of particles. But space-time, as described by general relativity, has no particles. It is smooth, continuous, infinitely divisible. That description cannot support emergence. So something must be missing. One of the strongest clues comes from quantum theory. Quantum mechanics teaches us that physical systems are not best described by positions and velocities, but by states in an abstract space. These states encode probabilities and correlations. Most importantly, they encode information. Over the past few decades, physicists have discovered that gravity behaves strangely when viewed through the lens of quantum information. Entanglement, in particular, has changed how gravity is understood. Entanglement is not a force. It does not transmit energy. It does not act locally. Yet, it creates correlations between distant systems that cannot be explained by classical physics. When two particles are entangled, the state of one cannot be fully described without the other, no matter how far apart they are. Initially, entanglement was treated as a curiosity. Then it became a resource. Now it is becoming a foundation. In certain theoretical models, space-time geometry itself appears to arise from patterns of entanglement. Distances are not primary. Connectivity is.
Two regions of space appear close not because they are nearby in some pre-existing geometry, but because their underlying quantum degrees of freedom are strongly entangled. In this view, geometry is not fundamental, it is a bookkeeping tool for entanglement structure. If space-time emerges from entanglement, then gravity, being curvature of space-time, emerges from changes in entanglement.
This idea is not metaphorical. In specific models of quantum gravity, altering entanglement changes geometry. Removing entanglement causes space-time to tear apart. One influential result shows that Einstein's equations can be derived from entanglement entropy constraints in quantum field theory. Space-time curvature appears as a response to how entanglement is distributed. This suggests something extraordinary. Gravity may be a manifestation of information flow, not matter pulling matter, not geometry guiding motion, but information reorganizing itself. In physics, a force traditionally does three things. It causes acceleration, it transmits influence, and it acts through fields or particles. Gravity fails all three tests at the fundamental level. In general relativity, freely falling objects experience no force at all. Locally, they move inertially. What appears as acceleration arises from comparing different inertial paths in curved spacetime. In emergent gravity scenarios, even space-time curvature loses its fundamental status. There is no field mediating gravity. There is no graviton in the usual sense, only collective behavior. This is similar to how sound behaves. Sound waves travel through air, but sound is not fundamental. There is no sound particle acting as a force between objects. Sound emerges from collective oscillations of molecules. If gravity is emergent, then searching for a fundamental quantum of gravity may be like searching for a quantum of sound. This does not mean quantization is useless. It means it may be applied at the wrong level. This is one reason quantum gravity has resisted unification for decades. We may be trying to quantize something that is not fundamental. Another deep clue comes from horizons. Horizons appear whenever information becomes inaccessible. Black hole horizons, cosmological horizons, and even accelerated observers experience horizons. In every case, horizons are associated with entropy and temperature. This universality is suspicious. Why should acceleration through empty space produce heat? The Unruh effect predicts that an accelerating observer will detect thermal radiation even in a vacuum. Nothing physical changes in the space-time itself, only the observer's state of motion changes. Yet, temperature appears. This strongly suggests that temperature, and therefore entropy, is tied to information access, not to physical substance. If gravity is connected to entropy gradients across horizons, then gravity is not acting on matter, it is acting on information availability. Matter moves in ways that preserve consistent information accounting across horizons. This reframes gravity as a bookkeeping requirement rather than a force. At this point, it becomes clear that gravity behaves more like an equation of state than a fundamental interaction. An equation of state relates macroscopic variables without specifying microscopic details. Pressure relates to volume and temperature without needing to know molecular structure. Einstein's equations may be doing the same thing. They may relate energy, geometry, and entropy without revealing the underlying degrees of freedom. This would explain why gravity is universal, why it couples to everything, why it cannot be shielded, why it resists quantization. Universality is a hallmark of emergent phenomena. Temperature does not care what atoms are made of. Pressure does not depend on chemistry. Gravity may not care about particle species because it does not act on particles, it acts on information. This view also sheds light on a long-standing mystery: why gravity is so weak. Compared to other interactions, gravity is absurdly feeble. The electromagnetic force between two electrons overwhelms their gravitational attraction by an enormous factor. If gravity were fundamental, this weakness would require explanation. If gravity is emergent, its weakness is natural. Emergent forces are typically weaker than microscopic interactions. Sound waves are slower than molecular motion. Elastic forces are weaker than atomic bonds. Gravity's weakness may reflect the fact that it is a collective effect spread across vast numbers of degrees of freedom. The implications extend further. If gravity is emergent, then space-time itself may not exist at the deepest level. There may be no before the universe in the usual sense, no background arena in which physics unfolds. Instead, space-time may crystallize out of quantum information as the universe evolves. This reframes cosmology entirely. The early universe may not have been small in space, but simple in information structure. Expansion may reflect increasing entanglement complexity rather than objects moving apart in pre-existing space. In this picture, the Big Bang is not an explosion in space. It is the beginning of space-time. Once gravity is no longer treated as a fundamental force, inertia itself comes under suspicion. In Newtonian physics, inertia and gravity are separate concepts. Inertia resists acceleration. Gravity causes acceleration. They just happen to be proportional, a coincidence encoded in the equivalence principle. Einstein elevated that coincidence into a principle. Gravitational mass and inertial mass are the same. Locally, gravity can be transformed away by free fall. An observer in free fall feels no force at all. But if gravity is emergent, then inertia may be emergent as well. This idea sounds radical, but it has a subtle motivation. Inertia has always been mysterious. Why does an object resist acceleration? Why should matter care about changing its state of motion? Classical physics never answered this. It simply stated inertia as a fact. In an emergent framework, inertia may arise from how matter interacts with the underlying microscopic structure of space-time. Accelerating an object may require rearranging information stored in space-time degrees of freedom. Resistance to acceleration would then reflect resistance to reconfiguration. In other words, inertia may be the drag imposed by information. This interpretation aligns with a deeper principle. Motion is not fundamental. Change is. Acceleration represents a change in relational information between systems. The universe may resist rapid reconfiguration not through force, but through entropy constraints. This brings us to a surprising consequence. Gravity and inertia may not be separate phenomena at all. They may be two expressions of the same underlying informational dynamics. If true, this would explain why they are inseparable in experiments and why the equivalence principle holds so universally. It would also explain why gravity appears geometrical while other interactions do not. Geometry may simply be the macroscopic language we use to describe stable information relationships. At this stage, it becomes useful to examine dark energy from an emergent perspective. In standard cosmology, dark energy is introduced as an additional component of the universe, an unknown form of energy that causes accelerated expansion. This approach treats acceleration as something that must be added, but if gravity is emergent, acceleration may arise naturally from entropy gradients at cosmic scales. In thermodynamics, systems evolve toward equilibrium, but in expanding systems, equilibrium itself can change. The universe is not a closed box. Its horizons evolve. Information accessibility changes over time. From this point of view, cosmic acceleration may not require a new energy component. It may be the natural tendency of spacetime to maximize entropy under horizon constraints. This does not eliminate dark energy models, but it reframes them. Instead of asking what dark energy is made of, the question becomes, what information balance does accelerated expansion enforce? This shift in question is subtle but powerful. Another deep implication concerns locality. Fundamental forces are local. They act through fields that propagate influence at finite speed. Even quantum field theory preserves locality at the level of interactions. Emergent gravity does not need locality. If gravity arises from global information constraints, then its effects may appear local while being fundamentally non-local. This does not violate causality. It changes what causality operates on. Entanglement already provides a working example.
Entangled systems exhibit correlations that are not mediated by signals. They do not transmit information faster than light, but they are not built from local causes either. Gravity may operate in a similar way. This would explain why attempts to construct a local quantum field theory of gravity encounter infinities and inconsistencies. The assumption of locality may be wrong at the foundational level. This perspective also casts new light on singularities. In general relativity, singularities represent points where curvature becomes infinite and the theory breaks down. Black hole centers and the Big Bang are examples. In an emergent framework, singularities may not represent physical infinities. They may represent the breakdown of the macroscopic description. Just as temperature becomes meaningless for a single particle, space-time curvature may become meaningless when underlying degrees of freedom no longer support a geometric description. Singularities may mark phase transitions rather than physical catastrophes. This is not a minor reinterpretation. It changes what breakdown of physics means. It suggests that singularities are not failures of nature, but failures of language. Now consider gravitational waves. In standard physics, gravitational waves are ripples in space-time geometry propagating at the speed of light. They carry energy. They stretch and compress space as they pass. These observations are real and experimentally verified. But emergence does not deny them. Sound waves exist. They propagate, they carry energy, yet sound is not fundamental. Gravitational waves may be collective excitations of spacetime's microscopic degrees of freedom. They are not fundamental particles. They are organized disturbances. This aligns naturally with their weakness and their inability to be shielded. Collective modes are hard to block because they are not interactions between discrete objects. At this level, gravity begins to resemble condensed matter physics more than particle physics. Spacetime becomes analogous to a material with elastic properties. Curvature becomes strain. Energy becomes stress. Einstein's equations resemble constitutive relations. This analogy is not poetic, it is mathematical. Several approaches to quantum gravity explicitly model spacetime as a many-body system with emergent geometry. The challenge is not conceptual, it is technical. We do not yet know the microscopic constituents. But history suggests this should not surprise us. Before atomic theory, heat existed without atoms, pressure existed without molecules, elasticity existed without lattice models. Physics often discovers macroscopic laws before microscopic explanations. Gravity may be another case. This view also changes the role of symmetries. Fundamental forces are defined by symmetry principles. Gauge symmetries dictate interactions. Conservation laws follow. Emergent phenomena do not obey symmetries fundamentally. They inherit approximate symmetries at large scales. If gravity is emergent, its symmetries may not be exact, they may be effective. This could explain why general relativity works so well while still being incompatible with quantum mechanics. It may be an effective theory, not a final one.
One of the most unsettling consequences of this framework is that spacetime may not exist everywhere. Regions of extremely low entanglement may not support geometry at all. Spacetime could dissolve under certain conditions. This possibility has implications for black hole interiors, the early universe, and potentially even vacuum states. Reality may not be uniformly real. If gravity is an emergent phenomenon tied to information and entropy, then black holes stop being exotic exceptions and instead become central laboratories. In traditional thinking, black holes are extreme gravitational objects. In emergent thinking, they're extreme information objects. A black hole does not simply trap matter, it limits information. The event horizon is not a physical surface, but a boundary of accessibility. Beyond it, correlations are cut off for outside observers. What matters is not what is inside, but what can be known. This is why black hole entropy scales with area. Entropy counts the number of microscopic configurations consistent with what an observer can access. The horizon defines that access. Area is not geometry here, it is bookkeeping. Once this is accepted, the so-called black hole information paradox changes character. The paradox assumes spacetime is fundamental and information must fit inside it. Emergent gravity reverses the logic. Spacetime itself must reorganize to preserve information accounting. Information is not stored in spacetime. Spacetime is how information is organized. This perspective explains why attempts to localize information inside black holes fail. Localization is a geometric concept. Information is not geometric at the deepest level. Reference Leonard Susskind, The World as a Hologram, Journal of Mathematical Physics, 1995. Now consider motion again, but remove geometry entirely from the picture. Imagine describing the universe purely as a network of quantum states with evolving correlations. There's no background space, no distances, only relationships. In such a system, what does it mean for something to move? It means correlations change. What does it mean for something to accelerate? It means correlations change in a way that resists the existing informational structure. Gravity, then, is not motion through space, it is reconfiguration within a network. Objects fall because the global informational network allows more consistent configurations when correlations align in certain ways. This is not metaphor. In tensor network models of spacetime, geometry emerges from how quantum states are connected. Changing connectivity changes curvature. Curvature guides motion. The force disappears. Only consistency remains. This leads to a sharp reinterpretation of the equivalence principle. In classical language, the equivalence principle says gravitational and inertial effects are locally indistinguishable. In emergent language, this is inevitable. If inertia and gravity both arise from the same underlying informational resistance, then there is nothing to distinguish. They are the same phenomenon seen from different relational perspectives. The equivalence principle is not a coincidence, it is a diagnostic. It tells us we are already using an emergent description. Another subtle point now comes into focus: energy. In general relativity, defining gravitational energy is notoriously difficult. There is no unique local energy density for the gravitational field. Energy conservation becomes ambiguous in curved spacetime. This is often treated as a technical inconvenience. In emergent gravity, it is expected. Energy is a concept defined relative to time translation symmetry. If time itself is emergent, then energy cannot be fundamental. Gravitational energy resists localization because it is not a substance, it is a global constraint on information flow. This explains why gravitational energy can be transformed away locally but reappears globally. It is not something that exists at a point. Now consider cosmological expansion again, but without invoking dark energy as a substance. In an information-based universe, expansion corresponds to increasing capacity for correlations. As horizons evolve, the number of accessible states changes. Accelerated expansion may reflect a phase where the universe is increasing its informational degrees of freedom faster than matter can equilibrate. This makes cosmic acceleration less mysterious and more structural. It also suggests that expansion is not something happening in spacetime, it is something happening to spacetime's informational substrate. At this depth, the question, what is spacetime made of, becomes ill-posed. Spacetime is not made of anything. It is what information looks like when it is coarse-grained. Just as temperature is not made of heat particles, spacetime is not made of spacetime particles. Attempts to find fundamental spacetime atoms may be misdirected. The correct question may be, what patterns of entanglement are stable enough to appear geometric? This has consequences for causality. In a fundamental spacetime, causality is built into the geometry. Light cones define what can influence what. In an emergent spacetime, causality itself may be emergent. At the deepest level, correlations need not respect geometric ordering. Only when spacetime emerges do causal structures appear. This does not allow paradoxes because information transfer is still constrained, but the constraints arise statistically, not geometrically. Causality becomes a large-scale regularity, not a microscopic rule. At this point, the word illusion must be handled carefully. Gravity is not illusory in the sense of being unreal. Emergent phenomena are real. Temperature is real. Sound is real. Pressure is real. They just do not exist at the fundamental level.
Gravity may be exactly like that. It exists where spacetime exists. It disappears where spacetime dissolves. It has no meaning where information has not yet organized itself into geometry.
This framework also changes how we interpret experiments. Precision tests of gravity confirm general relativity to extraordinary accuracy. This does not threaten emergent gravity. Emergent theories reproduce macroscopic laws extremely well. Fluid dynamics works perfectly without knowing atomic details. General relativity may be the hydrodynamics of spacetime. There is an uncomfortable implication here. If gravity is emergent, then spacetime itself may have limits of validity. There may be regimes where geometry stops being a useful concept altogether. This is not merely at singularities. It may occur wherever entanglement structure becomes sparse or unstable. The universe may contain regions where has no meaning. At this depth, the idea of gravity as probability rather than force becomes unavoidable. In classical mechanics, probability enters only because of ignorance. If you know all positions and velocities, motion is deterministic. Probability reflects lack of information. But in modern physics, probability is fundamental. Quantum mechanics does not allow perfect prediction even in principle. The universe itself evolves probabilistically. If spacetime emerges from quantum information, then probability is not an add-on, it is structural. This changes how motion must be understood. An object moving in what we call a gravitational field is not responding to a cause, it is following a bias. The bias is statistical, not directional. Down is not a place, it is a higher density of allowed microstates. This is subtle but critical. In thermodynamics, systems evolve toward states with overwhelmingly more realizations. This is not because the system prefers them, it is because alternatives are vanishingly rare. Gravity may operate the same way. Given a configuration of information that supports spacetime, certain rearrangements are vastly more probable than others. Matter does not fall because it is attracted, it falls because remaining suspended corresponds to fewer consistent informational configurations. Motion is selection, not propulsion. This resolves a long-standing conceptual tension. In Newtonian gravity, force acts instantaneously at a distance. In relativity, geometry replaces force but introduces global constraints. In emergent gravity, neither instantaneous action nor geometric compulsion is fundamental. Instead, global consistency determines local behavior. This is why gravity is universal. It does not act on charge, spin, or internal structure, it acts on existence within spacetime. Anything that participates in information organization participates in gravity. There is no way to opt out. Now consider why mass curves spacetime in the first place. In standard language, mass tells spacetime how to curve, but that statement hides the mechanism. From an informational perspective, mass corresponds to localized energy, and energy corresponds to constraints on state evolution. Highly constrained systems reduce the number of available microstates nearby. This reduction distorts the informational landscape. Spacetime curvature may be nothing more than the macroscopic imprint of this distortion. Matter does not create curvature because it is heavy, it creates curvature because it restricts information flow. This leads to a reinterpretation of gravitational time dilation. Clocks run slower near massive objects. Traditionally, this is explained geometrically, time is warped. But in an emergent framework, time itself is not fundamental, it is a measure of change. If information rearranges more slowly near constrained regions, then fewer distinguishable states pass per unit parameter, time appears to slow. No force is acting on clocks, no field is influencing mechanisms, the rate of change itself is altered. Time dilation becomes a statement about information processing speed. At this point, the distinction between dynamics and kinematics begins to dissolve. In fundamental physics, kinematics describes what motion is allowed, dynamics describes why motion happens. In emergent gravity, there may be no such separation. What is allowed is what happens. The universe does not compute trajectories, it relaxes constraints. This perspective also reframes the role of equations. Einstein's equations do not tell spacetime what to do, they summarize how spacetime behaves when information is organized in stable ways.
They are descriptive, not prescriptive. This explains their elegance and rigidity. Effective laws often appear simple because complexity has already been averaged out. Now consider a question that sounds philosophical but is physically sharp. Why does the universe exist in a state where gravity emerges at all? Why does information organize itself into something geometric? One answer may lie in stability. Certain patterns of entanglement may be dynamically favored. They resist decoherence. They persist. Geometry may be a phase of quantum information. Just as solids, liquids, and gases are phases of matter, spacetime may be a phase of information. Gravity would then be a property of that phase, not a fundamental interaction. Phase transitions become crucial. The early universe may represent a transition into a geometric phase. Before that, there may have been no space, no time, no gravity, only correlations.
This makes the Big Bang less mysterious and more radical. It is not a moment in time, it is the emergence of time. It is not an explosion in space, it is the birth of space. In such a transition, asking what came before becomes meaningless. Before requires time. Time is what emerged. This framework also reframes quantum fluctuations. Vacuum fluctuations are often described as particles popping in and out of existence. That language assumes space-time as a backdrop. In emergent gravity, fluctuations are changes in informational structure. What appears as particle creation may be a local excitation of relational patterns. Particles become secondary. Fields become secondary. Relationships become primary. Now consider what this does to the notion of reality. If space-time is emergent, then reality is not a collection of objects in space. It is a web of constraints that stabilize into geometry. Existence becomes relational. An object exists not because it occupies space, but because it participates consistently in the informational structure. This has consequences for identity. Objects do not persist because they are the same substance. They persist because their relational patterns are stable over time. At this depth, gravity no longer looks like something the universe has. It looks like something the universe does. Not actively, not deliberately, automatically. There is one more subtle implication that rarely gets discussed. If gravity is emergent, then it may not be symmetric in time at the deepest level. Fundamental forces are time reversal invariant. Gravity, when understood geometrically, also appears time symmetric. But entropy is not. If gravity arises from entropy gradients, then its apparent time symmetry may be approximate. This could connect gravity to the arrow of time in a way no fundamental force ever has. Gravity may not just coexist with time's arrow, it may help define it. Reference: E. Verlande, On the Origin of Gravity and the Laws of Newton, Journal of High Energy Physics, 2011. At this depth, the notion of a law of nature itself becomes unstable. In fundamental physics, laws are assumed to be absolute. They exist independently of the systems they govern. They do not change. They are not negotiated. But emergent phenomena do not obey laws in this sense. Fluid dynamics has laws, yet those laws are not written into the universe. They arise because large collections of molecules behave in statistically regular ways. Change the microscopic structure enough, and the effective laws change. If gravity is emergent, then Einstein's equations are not laws etched into reality. They are regularities that appear when information organizes itself into a geometric phase. This reframes physics profoundly. Instead of asking what law governs gravity, the deeper question becomes what conditions make gravity inevitable. Gravity would not be enforced, it would be unavoidable. This view also dissolves a long-standing puzzle: why gravity is so simple. Einstein's equations are compact, elegant, and rigid. There is little freedom to modify them without breaking consistency. This rigidity is often taken as evidence of fundamentality. In emergent systems, the opposite is true. Effective descriptions are often rigid precisely because they summarize enormous complexity. There are many ways for microscopic behavior to vary, but only a few ways for macroscopic stability to exist.
Gravity's simplicity may be the signature of deep averaging. Now consider scale. Fundamental interactions operate at all scales. Electromagnetism works the same way whether you study atoms or galaxies. Gravity does not. At very small scales, gravity becomes negligible. At very large scales, it dominates structure. This scale dependence is unusual for a fundamental force. In an emergent picture, it is expected. Emergent effects require many degrees of freedom. At small scales, there are not enough to support geometric behavior. Gravity weakens not because the force is small, but because the description breaks down. Below a certain scale, gravity may not exist at all. This has consequences for quantum gravity research. Most approaches assume space-time exists and attempt to quantize it. They treat geometry as fundamental and apply quantum rules to it. If space-time is emergent, this approach is inverted. One should not quantize space-time. One should identify the quantum system whose collective behavior looks like spacetime. The failure to observe gravitons may not be technological, it may be conceptual. Gravitons may not exist as particles any more than phonons exist as fundamental entities. They are excitations of an effective medium. At this depth, the universe begins to resemble a computation, but not a digital one. Not a simulation running on a background machine. A self-consistent evolution of information constrained by consistency, stability, and entropy. There is no program, no external processor, no clock. Time emerges as ordering of change. Space emerges as stable relational structure. Gravity emerges as bias toward consistency. Now consider a question that seems abstract but has sharp implications. Why does information organize at all? Why does the universe not remain in a maximally disordered, non-geometric state? One possible answer lies in error correction. Quantum information theory has revealed that certain patterns of entanglement are robust. They protect information against noise. They stabilize correlations. Remarkably, space-time geometry appears to have error-correcting properties. Information stored in one region can be reconstructed from another. Local disturbances do not destroy global structure. This is not an analogy. It is mathematically precise in certain models. Space-time may exist because it is good at preserving information. Gravity may be the cost of that preservation. This reframes curvature. Curvature is not bending, it is redundancy. Regions of space-time overlap informationally. This overlap produces resilience. Curvature measures how much redundancy is required to maintain consistency. Strong gravity corresponds to extreme error correction. Black holes are the ultimate error-correcting structures. They hide information so efficiently that geometry collapses into a horizon. Now revisit the question of force. A force implies agency. It implies something acting on something else. Emergent gravity removes agency. Nothing pulls, nothing pushes. The universe relaxes. Objects move the way foam bubbles rearrange. The motion has direction, not because of intent, but because constraints make alternatives unstable. This also explains why gravity cannot be shielded. Forces can be blocked, interactions can be screened. You cannot shield probability. You cannot insulate yourself from consistency. If you exist within spacetime, you participate in its informational accounting. Gravity is participation, not interaction.
At this depth, even the idea of object becomes questionable. Objects are stable bundles of relationships. They persist because their internal correlations are strong relative to their environment. Massive objects persist by heavily constraining nearby informational structure. This persistence manifests as curvature. Mass is not weight, it is influence over possibility. Now consider vacuum. In classical thinking, vacuum is empty space. In quantum field theory, vacuum is a sea of fluctuations. In emergent gravity, vacuum is neither empty nor full. It is the ground state of informational organization. Its energy is not something stored in space. It is the cost of maintaining spacetime itself. This reframes the cosmological constant problem. The enormous vacuum energy predicted by quantum field theory may not gravitate because it is not energy in spacetime, it is energy of spacetime.
Gravity responds only to deviations from equilibrium, not to the equilibrium itself. This idea has radical consequences. It suggests that most of what we call energy does not curve spacetime. Only information imbalance does. Motion is the universe updating itself. Curvature is the record of constraints. Time is the count of distinguishable updates. This also explains why gravity resists unification. You do not unify bookkeeping rules with interactions. You derive interactions within bookkeeping constraints. Gravity may not join the other forces because it is not a force at all. One final subtlety emerges here. If gravity is emergent, then it may not exist in all possible universes. Other informational phases may exist with no geometry, no curvature, no gravity. Our universe may be gravitational, not because gravity is inevitable, but because geometry is stable here. This makes gravity contingent, not necessary, not eternal, but appropriate.
At this point, the idea of explanation itself needs to be re-examined. In classical physics, to explain something means to identify a cause. A force causes motion. An interaction produces an effect. Explanation flows forward in a chain. Emergent gravity does not work this way. There is no single cause of falling, no agent responsible for curvature, no microscopic event that triggers gravity. Instead, explanation becomes structural. To explain gravity is to show that given certain informational conditions, gravity must appear. Not because something pushes matter, but because alternatives cannot remain stable. This is a different kind of explanation, closer to why pressure exists in gases or why temperature equilibrates. No molecule causes temperature, yet temperature is unavoidable. Gravity may belong to this category, inevitable but uncaused. This reframing quietly resolves a question that has haunted physics for centuries: why gravity is universal. Forces usually discriminate. Electromagnetism ignores neutral particles. The strong force works only at subatomic distances. Even quantum effects can be isolated. Gravity cannot be isolated. Everything with energy gravitates, even light, even vacuum fluctuations under certain conditions. If gravity were a force, this universality would be mysterious. If gravity is emergent, universality is automatic. Anything that participates in spacetime participates in gravity, because gravity is not something spacetime contains, it is something spacetime does. Another long-standing puzzle also dissolves: why gravity defines the structure of the universe at large scales. Galaxies form, clusters emerge, filaments stretch across cosmic distances. Gravity shapes everything bigger than stars. If gravity were just another force, this dominance would be surprising given its weakness. In an emergent framework, gravity dominates large scales precisely because it is collective. It becomes more coherent, not less, as systems grow. At small scales, geometry dissolves. At large scales, geometry becomes rigid. This is the opposite behavior of fundamental interactions. Now consider what this implies about certainty. If gravity is emergent, then space-time itself may be approximate. Distances, durations, and trajectories may not be exact quantities at the deepest level. They may be averages. This introduces a subtle but profound humility into physics. Our most precise measurements may be measuring spatial approximations, not exact truths. Reality may not be sharply defined at the foundation. It may only become sharp when enough information aligns. This leads naturally to the question of limits. Where does gravity stop? Not in the sense of range, but in the sense of meaning. Below certain scales, falling may not exist. Before and after may not exist. Here and there may not exist. These are not failures of theory, they are boundaries of applicability. Just as temperature ceases to make sense for a single particle, gravity may cease to make sense where space-time itself is no longer a valid description. At this depth, the phrase "gravity is an illusion" can finally be understood correctly. It does not mean gravity is unreal, it means gravity is not fundamental.
It means gravity is a consequence, not a cause. It means gravity is what remains when countless microscopic relationships are averaged into something stable enough to look geometric. The illusion is not gravity. The illusion is that force is the right language to describe it. Now, step back and look at what has happened. Newton described gravity as attraction. Einstein replaced attraction with geometry. Emergent gravity replaces geometry with information. Each step removes something assumed to be fundamental. First force, then space, now even space-time itself. What remains is not emptiness, but structure, relationships evolving under constraints. This does not mean physics is finished. It means physics is changing its questions. Instead of asking what force causes gravity, the question becomes, what kind of informational universe makes gravity unavoidable? Instead of asking how space-time curves, the question becomes, why does information organize itself geometrically at all? And this is where the idea quietly reaches its end, not with a final answer, but with a shift in perspective. Gravity may not be something the universe has. Gravity may be something the universe becomes when information organizes itself in a stable, coherent way. Objects do not fall because they are pulled. They fall because in a universe like ours, there are overwhelmingly more ways to fall than to remain suspended. No force, no intention, no command. Just consistency, just probability, just the quiet mathematics of what can exist and what cannot.